So, good afternoon, everyone. I am Praveen Ambasta, General Manager System Technology. And yes, as Vedika has given you the information about the artificial intelligence, machine learning, supervised learning, unsupervised learning, neural model, and all. So, as you know, our department is system technology. So, we are also using artificial intelligence, machine learning for many of our module. So I am starting my presentation. So I'm sharing my presentation. Yeah. So first, so the very first I would like to tell you that what are the modules in which we are using artificial intelligence or machine learning. First is our data validation system. So what is data validation system? How artificial intelligence or you say neural model is being used in data validation, that I will explain you. Second thing is we are using this artificial intelligence for predictive analysis of the fault. Means well before the fault occur. So what is the way how we create KPI, how we take the data. So all those things I will explain in detail. Then boiler cleaning management. So in boiler cleaning management also we are using this technology, AI technology. So when to do the soot blowing, whether the boiler is dirty or not dirty, whether you require the soot blowing or you don't require the soot blowing, what is the methodology that I will explain you. Then we are using it for our cool matrix. Then we are using it for the boiler tube leakages. So how this AI is helping us to predict the boiler tube leakages. So that I will explain you. And then coal selection matrix means in the coal yard also we are using AI technology for the coal selection matrix. So these things I would like to cover. And then I think then you'll be able to know that yes, how we are using AI and especially STIAG, how STIAG is doing also this AI technology in our digitalization field. So first thing, as you know, digital twin. So I would like to show you what is this digital twin. So this digital twin you can see in here. So this is basically epsilon model. This is the digital twin. Is basically 800 megawatt of one of the Gujarat plant digital twin. So here you can see this is the cycle side of the plant. This is HP, IP, and LP turbine. Then we are having it's 800 megawatt digital twin, and then we are having the LP heater side. Then we are having deaerator, and then we are having turbo driven pump. On the left side, we are having HP heater side. So this is the cycle, and then on the very left, we are having the boiler. So this is the furnace. And then we are having Platon superheater, final reheater, final superheater, then LTRH, then economizer. So these are the milling area at the bottom. And then we are having air heater. These are the fans area, ESP, ID fan, and then a stack. So this is the digital twin of one of the Gujarat plant 800 megawatt digital twin. And this model is basically developed in a software Epsilon. Epsilon, you must know that this is a stack software. And the whole development is being done in Swingenberg, Germany. And we are having the licenses. We supply the CMS central monitoring system. We supply the PARDO system to NTPC and the non-NTPC power plants. So behind all the calculation, this digital twin we use. And here, this virtual plant, we prepare the virtual plant, and this virtual plant runs with the plant data. As your plant runs in the plant, the same with the same data, we run the virtual plant and we give you the output that what about the performance of your boiler, What about the performance of your turbine, condenser, pump, heater, everything? So this is the digital twin that I wanted to show you. And yes, behind this digital twin, we use the AI model. So first the thing is, whatever you want to do AI model or anything, it requires data. So how we take the data from a power plant? So of course, we require the architecture is like this. Just a moment. So you must have a DCS system. You require a DCS system to take the data. And then from the DCS system, you must have a OPC interface. So from the OPC interface, we take the data. So the whosoever is the OEM of the DCS, they provide you a OPC so that any of the third party can take the data from the DCS system. So this is the DCS system, and from the DCS system, we take the data from the OPC interface to our data management system. Data management system where we are going to store the data. Of course, in from Stack, we are having the data management system that is known as SRX. We are having the data management system SRX. And yes, once we are having the data management system, then we give this data to the digital twin or to any of the module for to run. Then we, of course, we prepare the AI model for different module. So first thing is data validation system. As you know, that in a power plant, let us suppose we are taking 1,000 data. So you know that there are many data which is bad, and it becomes bad with respect to the time and all. So what we do, we collect the data for 6 months, 1 year at different load conditions. And if any updated the data becomes bad from the AI model, from the neural model, we replace the bad data with the good data. So how it is done, I will show you some of the examples. Yes. So once data validation is done, then it goes to the different module for calculations and all. And then we show you the results in our visualization screen. And then we are having offline what if and all. So for any of AI model and all, you require data. And that the source of the data is DCS. So if any of the plant you want to install your AI or you want to have the digitalization, DCS is must. Without DCS system, without OPC interface, we cannot do digitalization. We cannot install any of the advanced AI/ML solution or anything. So DCS is the must. Yes. Now, so of course, digital twin is going to depend upon first principle of thermodynamics and neural network. So what is neural network? As Vedika has already explained you that you are having the input. Just I am opening my neural model so that it will be more clear. Yes. So what we can see in a neural model, as Vedika has explained you, that you are having the input layer. Then you are having the hidden layer, and then you are having the output layer. So in the input layer, you are having the input and you provide some weightage to the input layer. Then it process in the hidden layer. Then you are having the output layer. So in the output layer, you check that whether your weightage is correct or not. If is your because you know the output. If let us suppose I am having a I know that my main steam temperature is 540 degrees centigrade. And if let us suppose I am having four measurement of main steam temperature, two is 532, 538, and one is let us suppose 240 or 280. So I know that this 280 degrees centigrade is false. So what it will do, it will replace with the neural model that yes, this is bad value. It will be replaced with the neural value. So what it go to the neural model and try to find out that under this circumstances, under this load condition, under this vacuum, under this situation, what will be the best fit, and accordingly it finds the best fit and finds the value for the bad one. So I can see it's a three-tier process: neural model, neural network, and all. And then I will show you some of the examples of neural network. This is one of the NTPC power plant. So here, this you can say that primary air temperature after your air heater. So one of the 70 HFE 40 CT 108 XQ03, it is bad. And one of the temperature, it is 323. You can see the upper one, PA out 3, this is 323, and this 70, it is nan value. So here I can see that this PAHB empty PA out underscore V means it is validated. It is replaced with a neural one, and this is basically 323 degrees centigrade. So here we can see that the primary air temperature after air heater, let us suppose I am having a 4 value, one is bad, and out of the three is okay, but fourth is bad, but I have to do the calculation and it should be the average one. So what it will do, the bad one will try to find its best fit from the neural model, and then it will be replaced from the neural one. So neural, of course, we are having the data for 1 year under different load conditions and all. So it will try to find out that under this condition, what will be my primary air temperature with best fit, and believe that generally we find very good results from this neural model. And this is our with this we can see that let us suppose I am having a raw measurement and I am having a value from my data reconciliation. Let us suppose this is the green one. And then we are having the precise measurement. Precise measurement means measurement when we put some special equipment. Let us suppose we are doing PG test or something like that. Then we can see that our data reconciliation means the data which is coming from the neural model and the data which is very precise. It's a very close. It's a very close, and we have seen that for the bad data, we use this neural model, and it's having a very good fit. So whenever we are having the bad data, of course, generally in a power plant, wherever we install our performance monitoring and all, so we do not do the data validation or we do not make the neural model for like megawatt, then condenser vacuum, my coal mass flow, and of course, the flue gas temperature after economizer, which are very, very vital, oxygen after economizer. So we do not make the neural model for this one, but for the extraction side pressure temperature, or you can say the temperature of the feed water condensate side. So all then the steam side. So all those measurement we make the neural model. And we find that yes, neural model is very, very well fitted and it is well replaced with the yeah. And yes, but this is not the final one. We don't tell that, yes, our solution will run with the neural model only. No, we give to the list to the CNI engineer that, yes, these are the value we are replacing from our neural model. So kindly correct those measurement. So it's duty of the CNI engineer to correct those measurement so that the solution will be able to give you a right result. And of course, the learning should be continuous, because whatever once you have trained the neural model, it doesn't mean that it will be continuous forever. As Dr. Vedika also told that it's a continuous process, so you'll have to train the model regularly. Of course, we generally put it in auto train so that the training will be continuous and we shall have the results in means continuous process with the latest data. So this is the how we use the neural model for our data validation system. So data validation is one of the very important thing, because when you don't have a correct data, you cannot have a correct result. So, but of course, as our experience and all, we cannot have all the data, correct data from a power plant. Let us suppose we are pulling 1000 data or 1500. There will be bad data. So we must have a replacement. And for the replacement, neural model is the best one. Yes. And now I am coming to my second topic, that is boiler cleaning management. So how my neural model is using, we are using for my boiler cleaning management. So yes. So yes, whenever we show you in our solution that if the color is red, it means the surface is dirty, you require the soot blowing. If my surface is yellow, it means the condition is suboptimal. Means it is going to deteriorate, means you require soot blowing later. And then it is green, means if the surface is completely clean, you don't require the soot blowing. So this is a way we, with the traffic light system, we show you the condition of the heating surfaces. Yes. So what is the problem with the soot blowing? Why we require the soot blowing? So first thing is that when our surface is not clean, then we are having a very high flue gas temperature at the end, and we are having a high dry gas loss. Second thing, we must have a high superheater and reheater spray flow. And of course, if there will be lots of slag and all, we can have a unplanned shutdowns, damage of the ash hoopers and all. So yes, we soot blowing is one of the very important thing. And if my surface is clean, in spite of that, I am doing the soot blowing, I am having a high cost because we are using a very high costly steam. During the soot blowing, generally we tap the steam from the superheater area or the PRDS area. So generally from the superheater area. So it's a very high pressure temperature steam. It's a very high costly steam. So we are basically wasting the steam when the surface is clean. And since we are putting this high pressure temperature steam on the heating surfaces, so we are having a lot of erosion of the tubes also. So erosion is also there. And so the aim should be when the surface is really dirty, we do the soot blowing. And if the surface is not dirty, we do not do the soot blowing. So, but how? How we shall be able to know that, yes, this is the condition of the surfaces, you do the soot blowing or you don't do the soot blowing. So first I would like to tell you that we calculate the heating surface efficiency. So how heating surface efficiency is being calculated, I will show you something. So yes, this soot blowing module, it gives you the information that how much is the current degree of falling, how much is the falling, whether the falling is 50%, 60%, 80%, how much. And of course, digital twin is being used, neural model is being used to find out the degree of the falling. And second is the cost optimization. So in BCM module, we use the digital twin, we use the neural model, we use the fuzzy logic, fuzzy controller to give us the information that whether my surface is dirty or not dirty. Yeah. So what are the criteria? What are the criteria that is being taken into account that we do the soot blowing or we don't do the soot blowing? What is the how a fuzzy model works? So the criteria is first is heating surface efficiency, that whether the surface is dirty or not dirty, that is being calculated, and that is very, very important also. Second thing is reheater spray flow. How much is your reheater spray flow? Then flue gas temperature at the back end, means after air heater. What about the flue gas temperature. Then we take into account some of the cost also, that what is the suit blowing cost. Then we have what about the interaction with the neighboring suit blower level. Then what is our sequence of suit blowing? How do we do? Because generally in the water valve, we do from the bottom to the top. And then generally in every power plant, I can see that there is a suit blowing in every shift. At least in 24 hours, they must go for the suit blowing. And for the LRSB and all, they go for a week and all. But for the wall blowing, they generally have the suit blowing in every 8 hours, or generally have the suit blowing in every 24 hour. So these are the criteria. These are the criteria, and of course, one of the criteria is the time. Time is generally your OEM recommend you that you must have the suit blowing in 8 hours or minimums or maximum 24 hours. So one of the criteria is, of course, not only the efficiency or the spray flow or the back end temperature. We take into account the time criteria also, that is being given by the OEM, by the manufacturer, by the boiler manufacturer.